Okay, so I told you we would get to part 2. So we talked about whether endothermic or exothermic a little bit. Temperature changes cause things to be spontaneous or not. Also, there is this thing called entropy. Hi, this is our second important factor, and that is entropy. So entropy is with an S. Enthalpy was heat. That's an H, delta H. Entropy is an S, or change in enthalpy is delta S. Those are the two main factors that play into things being spontaneous or not. Okay, so this is the second quantity involved in thermodynamics, or the favorability. What is entropy? Entropy is a measurement of the, I'm gonna kind of like put it in quotes, randomness of a system. Okay, so a highly ordered system, okay, is essentially very, very low entropy. Okay, so the highly ordered would be low entropy. Okay, there's not a lot of chaos, there's not a lot of randomness. However, anything that is very disordered or spread out or chaotic or what would have high entropy. Okay, so like I'm going to use a bedroom as an example. After you've cleaned your room, you put everything away. That is very highly ordered. It would be low entropy. High entropy would be if you have everything all over the place. Okay, entropy in itself is a state function. We talked about these in 161. Okay, like energy or enthalpy, the process to get there doesn't actually matter. It's just final minus initial. So delta S is S final minus S initial. So the measurement of orderness of the final stuff minus the initial stuff. You can actually calculate it based on Q over T, or heat per temperature, or delta H over T. And the units for delta S are going to be joules per Kelvin mole. Okay, so again, I'm looking at this picture over here. Something has greater entropy if it's got more molecules, and they're different molecules. There's more spaces they can be. It's got less entropy if you have less molecules and like they all look the same, for example. Okay, this is true. We're not going to use this equation very much, but this is true for reversible processes. Okay, so you can actually calculate how ordered or not ordered it is if you know the heat change associated with it. This is going to be important. You need to make sure that we get the right units when we're talking about entropy. Okay. So I do have an example problem based on that equation up there. Like I said, we're not going to be using it much, but we can. So example number 1, what is the entropy change, delta S, for melting ice at 0 degrees Celsius? What about freezing water at 0 degrees Celsius? And I gave you the delta H fusion for ice is 6.01 kilojoules per mole. Well, we know what melting is, and we know what freezing is, right? Melting would be going from solid to liquid. Freezing would be going from liquid to solid. Okay. And we know this changes at 0 degrees Celsius. Anything above solid to liquid is spontaneous. Anything below liquid to solid is spontaneous. Okay. So I gave you this new value. This is delta H fusion. That's the energy or the heat associated with fusing, or essentially turning into a solid, ice. Okay. So this is our value for melting / freezing. This is the energy per mole to melt or freeze ice, essentially. If you're putting energy in, that would be positive. If you're taking energy out, that would be negative. Okay, so I want to know what the delta S is. And I gave you this equation up here relating delta S to heat or Q or delta H, or however you want to say it, for this reaction. So the equation I gave you was that delta S equals delta H over T. Okay, now we do have to watch our units, right? You can't divide by 0. So delta S is delta H, not delta T. Oh, come on. H over T. Okay, so we can actually calculate this very easily. We're going to put delta H at fusion, so 6.01 kilojoules per mole, over the temperature. Now, remember, I told you this has to be, the unit should be joules per mole Kelvin, right? Look at those, joules per Kelvin mole or mole Kelvin. So I am going to have to convert these. My temperature does have to be in Kelvin. All right, so at 0 degrees Celsius, that's 273.15 Kelvin. Now, delta S is supposed to be in joules, so I am also going to convert that. I do 1 kilojoule is 1,000 joules. And I would get that the delta S for this process, either forward or backward, one's positive, one's negative, is, oh, well, okay, sorry, got it, is 24.7 joules per mole Kelvin. Okay, now it says, what is the entropy change for melting versus freezing? Now, essentially, these are reversible processes. One should be positive and one should be negative. So we are going to talk about what a positive delta S means versus a negative delta S. An increase in entropy would be things that are becoming more disordered. Okay, you're going to have more chaoticness, or however you want to say it. And that would be if we're going from a solid, which is highly ordered, to a liquid. So anytime we are melting, it should be becoming more entropic. So that is going to be a delta S is positive 24.7 joules per mole Kelvin. Whereas freezing is becoming more ordered or less entropic. The delta S is going to be negative 24.7 joules per mole Kelvin. All right. So positives and negatives in entropy, just like in enthalpy, mean different things if it's becoming more entropic or less entropic. Okay, so we're going to talk about these changes with entropy. There's kind of a law that goes with it, just like you can't create or destroy energy. The same thing applies to entropy. The delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. Again, it's kind of like heat, right? You can't create or destroy. When the delta S of the universe is greater than 0 joules per Kelvin, the process is spontaneous or favored. Okay, essentially, the universe tends toward chaos. It's easier to become chaotic than it is to organize things. Okay, so the delta S of the universe for something that is spontaneous is going to be greater than 0. So if it's positive, okay, that means it's becoming more entropic. That is favored. So positive is more entropy, more entropic, more chaos, that type of things. Okay. If delta S of the universe is less than 0, then the process is non-spontaneous or unfavored. Okay, this would be a negative or a more ordered, less entropy. Okay, essentially, it's harder to order things. You have to actually put in work to order things, right? Things can get messy. Go into your room, it gets messy on its own very easily, right? It actually takes work to put it back. So things that are greater than 0, delta S, are going to be spontaneous. Things that are negative, delta S, or more ordered, are going to be non-spontaneous. Okay, when delta S of the universe is 0, then the process is essentially at equilibrium, right? Or reversible. Either or can happen. Okay, so this brings us to the second law of thermodynamics, which has to do with entropy. And I've kind of already said this. We're just going to put it into more specific words. It is that the entropy of the universe is always increasing. It tends toward chaos, right? The entropy of the universe always increases. Okay, for a thermodynamically favored, aka spontaneous process. Okay, so I'm going to look at example number 2 here. Use the following data. Is the melting of ice at -1 thermodynamically favored? How about at 0 degrees, and how about at 1 degree Celsius? Now, you should be able to answer this question without actually doing any of the math. Right, at -1, things should freeze. At 0, we're at equilibrium, and at +1, things should melt. Okay, now we're going to do it mathematically. All right, I have the delta S of the system and the delta S of the surroundings at each of these temperatures. So if you actually calculate it, the change, or the system and the surroundings, right, we're going to calculate delta S of the universe. Delta S of the universe is the delta S of the system plus the delta S of the surroundings. So at -1, it would be negative 0.08. Okay, at 0 degrees Celsius, it's 0. And at +1, it would be positive 0.08 LTH of the unit. So we would say, well, positive is favored. Essentially, ice melts above 1 degree Celsius. Okay, at 0 degrees Celsius, we're at equilibrium, system and surroundings. And at negative 0.08, this would be not favored. Okay, so the melting of ice is not going to happen at negative 1 degree Celsius unless I were to put energy in. Okay, so that's essentially how the negative, positive, and 0 values play in. Now, what really is entropy measuring? I said like chaosness or disorder, but there's a little bit more to it than that. Again, especially if you take PChem, it really has to do with how the molecules are moving and how they could possibly move. So there are 3 ways that molecules can move. We're talking about kinetic energy of molecules. We're talking about the fact that they have translational, vibrational, and rotational motions. This is something you would really get into in taking PChem. Molecules can bend, they can stretch, they can rotate, they can move. Okay, all of these things play into the possibilities for our chaotic system, essentially. Okay, so when we're talking about heating, for example, whenever you heat something, I'm increasing the energy, I'm adding temperature in. What happens to the kinetic energy of those particles? Well, we know that the kinetic energy speeds up or is proportional to the temperature, right? You heat it up, the particles move faster, they move more. We know that. Okay? Kinetic energy is split up into 3 types of motion, the 3 types that we just said. So that kinetic energy is directly related to the temperature, how much energy is put in. Okay, so how do we look at that energy, that temperature, that chaos, and actually relate it to entropy? So you don't really need to know Ludwig Boltzmann's name, but Boltzmann is actually a type of distribution. He came up with this whole process to measure entropy, but it's this type of distribution that tells you how molecules are moving. So we will look at Boltzmann distributions, especially when we talk about gases. But he looked at the entropy from a statistical viewpoint. Okay, so the number of microstates, so if you've taken statistics, this might make a little bit more sense. But microstates are essentially like the possibilities, the possible places that things could be. Okay, so microstates are possible places. Depends on 2 things. Okay, so the chaos of the system, or how many possibilities it has, is based on the number of particles, okay, and the positions they can occupy. Okay, if you have more particles, there are more possible microstates. If you have more space, there are more possible microstates. So over here in this picture is really just an example of what I'm talking about on a very, very small scale. So if I have 4 different particles, right? See, they're all different colors. They can be in any of these possible microstates. I can have 2 on each side. I can have those same 2 on different sides. I can have 3 on one side and 1 on the other. And these are all those options. I can have the colors switching. These are all those options. I can have 3 on the right side and 1 on the left side, and then I could have all 4 on one side or all 4 on the other side. These are all of the possible microstates for these 4 particles. Now, if I introduce more particles into the mix, there would be more options. Or if I gave you a 3rd bulb that things could be in, you would have more options. So there are more microstates, meaning more entropy. Okay, so microstates and entropy go hand in hand. All right, so we're going to talk on a bigger scale. Consider 1 mole of gas at STP in a 1 liter container, right? So 1 liter. I've got a mole of gas, so 6.022 times 10 to the 23rd particles. If I allowed it to expand into a second 1 liter container, so I opened another space, I opened another bulb, that increases the entropy, okay? Because it has more positions, it has more possible microstates. All right, so we're gonna look at a couple more examples. What would happen to have more or less microstates if I have 4 molecules versus 2 molecules? Well, the answer would be 4 molecules, more possible microstates, more entropy. How about 2 decks of cards versus 1 deck of cards when you're shuffling? Well, 2 decks of cards have more possible microstates. So that means that I can have more entropy, there's more possible positions, all right? Now, how does this apply to life in general, how life came to be. Now, I'm not getting all philosophical on you, but I said that the universe tends toward chaos. Well, human beings and all life forms for that matter are actually very highly ordered, right? There are a lot of things that play into our systems working correctly and my body being able to act the way that it does. This is a highly ordered system, and it takes a lot to get us there. So according to the whole entropy thing, well, wouldn't it be that creating a human would be not favored? It would be non-thermodynamically favorable. Okay, this is not going to happen. So does this violate the second law of thermodynamics, that the universe tends toward chaos? How is it possible to actually make things more ordered? Well, the only way to do that is to add in work or energy. Okay? Add in energy or work. How do we create this highly ordered system? Well, we have to take in a lot of energy and work. When a mother's body is creating a human, she has to put in a lot of energy and work in order for that system to become ordered. Okay, so there is a lot that goes into it. It's not just the entropy, it also has to do with enthalpy. Okay, so both of those are important. Okay, a smaller example would be recharging a battery. If I'm recharging a battery with 100 kilojoules of useful energy, it will require more than 100 kilojoules of energy because, and this is kind of a little extra on there, the second law of thermodynamics. Second law. It's not that it just requires that amount of energy to get back. It's also that we have to order it all back together. So every energy transition results in a loss of energy, or we'll call it an energy tax. And it's really because of that entropy of a system. Okay, so we're going to talk about predicting entropy and how to actually calculate it here in the next video.